networks for computer vision.
Okay, thank you. So before I start, this is probably going to be less detailed than previous talks, because I'm introducing a slightly different topic to what other people have been talking about. I just want to preface it by saying that when I say alternative, I don't mean replacement. I mean something that can be used alongside neural networks, because they'll always have their place in research, literature, and practice. Something that can complement them and hopefully bring some new ideas to the table. So, many of you probably aren't familiar with GP. Many of you probably are. I'll just give you a really quick overview of it. So, genetic programming produces as its output a computer program. It represents
Speak up, please, especially to this side.
It represents programs as trees, abstract syntax trees. So you can see an example there, the abstract syntax tree. They get a lot more complicated than that, obviously, but the tree has function nodes which take inputs and terminal nodes which provide values. In GP, you generally have a population of individuals. Each individual is a program and it has a fitness value. So the fitness value tells you how well that program completes the task that you've assigned it. So the main process by which GP operates is that you have a set of generations. So that's encouraging. Each generation can be likened to an epoch with neural networks. So it calculates the fitness of each individual, keeps the best n individuals, combines pairs of other individuals, which we call the parents, to form new offspring, and then mutates a few individuals. So basically, after each generation, you have a new set of individuals where the best ones from the previous generation are kept, and the rest are produced from parts of the population. So, why do I think GP is a good idea for computer vision? Well, it's biologically inspired in that it mimics evolution, and this kind of ties into the talk that we just had from Andrew III. So, with neural networks, often it's quite a low-level mimicking of biology. So we mimic the structure of the brain down to the neuron level. With GP, we're more mimicking the evolution. So we're even mimicking how the solution is actually produced from a high level. And this gives us some benefits. It allows us to have human interpretable output. So we often find with the image-based GP that we have solutions that are using similar strategies to handcrafted solutions. So obviously in the olden days, before we had neural networks, a lot of solutions would be hand-coded. So if you needed to find a red cube in the scene, you would perhaps search for red pixels, find contours that define those red pixels, and then that would be your solution. You code that manually. GP tends to produce similar sort of solutions to that, but often to much more complicated problems. And the big key thing, I think, that relates to the talk that we just had is modularity and compositionality. That's kind of inbuilt to GP. So with GP you have a concept called ADFs, automatically defined functions. So what that means is you can learn one thing, and then you can use what you've just learned in the next set of learning. And you can do that either within one run of GP, or you can do a run of GP, get a solution, and then you can use that solution in the next run that you do. So you can learn what a cube looks like, you can learn what a red object looks like, and then you can learn to use those two solutions and combine them to learn what a red cube is. So in that way you've got your extra dimensions coming up, you've got red cubes, and red objects, and you can use as many or as few of those as you want. And actually, the nice thing about GP is you give it the functions that you've defined, and it finds the best way to use them. So there's no hand coding of anything. It's all automatically done, provided you give it the right operators to start with. So I'll talk a little bit about how we've applied GP to computer vision. So we've written a type GP system in which every function, parameter and terminal has a type. So what this means is the syntax trees that are constructed are syntactically valid, so every tree is guaranteed to be able to be executed. The functions are a vast array of small, simple operators, and they're things that you'll be quite familiar with when you've done computer vision programming. Fitness function in this GP system is one that simply attempts to match the class of as many output pixels to input pixels as possible. So inputs are annotated images. You give the system a mask which denotes the class for each pixel within the image. You don't need to annotate all pixels. Any unmarked pixels are ignored by the fitness measure, but can still be used by the functions, obviously. And we call the output of this GP system a vision system. So I said earlier that GP produces a program as its output. Well, this is slightly different in that it produces a set of programs, which I'll explain very shortly. And yeah, just to recap what I said, you give the system the training data, the operators, and it automatically optimizes the best way to use those and give you a solution. So the GP vision system that we produce has two stages, segmenter and classifier. Segmenter does the obvious. It segments the image to find which pixels belong to foreground objects and which pixels belong to background objects. That's an optional step. Obviously, not all problems can be segmented. They don't all need to be segmented. So if you had a small tile of, for example, breast cancer tissue, you don't need to segment that because the entire thing is worth considering. But if, for example, you were looking at objects on a table, you might want to segment the object out so that you're only considering that and not the background and not the table. It's stored as one or more programs made of the terminal nodes and operators that you originally supplied to train the GP system, and you can actually supply it images and video, and it will process those and give you classify objects within those. So the operators that we use, there are three main categories, and this sort of ties into biological inspiration as well. There's shape, colour and texture operators. I think there was a mention in one of the earlier talks about the different regions in the brain that I'm not a very neurologically clued up person, but I do know that there have been many papers that have shown shape, colour and texture have distinct regions in the brain which process them. So we sort of based our operators mainly around those. So, for example, in shape we've got global and local features. So I think someone mentioned earlier about global shape features not being particularly accessible by neural networks. Well, we've specifically programmed operators here that can access global shape features, local features as well, so perimeter, bumpiness, corner detections, edge detections, morphological operations, etc. There's a huge list of them. I can't obviously go into full detail here, but they all work together nicely to give some idea of shape. Colour, standard things, RGB, HSV, HSL, colour spaces, and then you can get the average, mean, median, convolutional operations, etc. Texture features as well are represented. And again, you've got some local features and some global features there. So what that allows you to do is, if you have an object which could be either smooth textured or particularly rough textured, then the GP could easily distinguish between those. Whereas if you have an image where the entire image has a particular texture, it can also do that because it's got the global texture measures. And of course, we've got many non-specific, non-image specific operators to help process numbers, give programs Boolean logic, etc. So programs generated by this GP system can have full if-then statements, and that's quite useful because that allows you to, if we come back to the compositionality argument, you could have a program that would automatically be generated that would say, right, does this scene contain a cube? Does it contain a red cube? Yes, no, and then you can go from there and do what you want with it. And that's really quite useful and quite powerful because what you start to get is the GP system automatically producing these quite large and complex programs to solve a variety of problems without any human intervention. So I don't want to make it sound like it's amazing in comparison to neural ropes because I think it's doing a different job. But for some of the tests that we've done, we've found that in comparison to most convolutional neural networks, which require thousands of images to get a good training set, perhaps fewer if you use augmentation, of course, with GP you're on average using a handful of images. So we're looking at about 5 images per class usually to get a very good classification rate. Training time, minutes and hours. I'll show you in a minute some results that we've got. Hardware, it's all CPU based, so it actually runs on standard Android mobile phone. I've evolved a classifier to classify what I'm going to show you in a minute in a little over half an hour, and it's generally robust to adversarial noise, perturbations, things like that. We generally don't see any issues with those, and I think that's probably because of the approach that we've taken with the biological operators. So successful trials, I'll just race through this quickly. We've done some various toy problems, and then big headline ones: detecting malaria in blood cells, distinguishing moles from melanomas, classifying histological breast tissue as cancerous or healthy, detecting whales in the ocean, and detecting land vehicles from airborne footage. Most recently, we've been working on segmenting and classifying corals from underwater images of coral reefs. That's really important for coral reef preservation. So the sort of case study I wanted to give you was malaria detection. You can see here we've got some examples of healthy red blood cells and some examples of infected ones. The task is to detect malaria in histological images. The data set we took from a similar paper by the NIH, 27,000 images. We used 7 for each class, and in just 11 minutes and 24 seconds we produced a classifier with 95% accuracy, 0.95 F1 score. The NIH paper achieved an accuracy of 95.7 and an F1 score of 0.957. So we're getting pretty close to the same accuracy as their pre-trained convolutional neural network. So I think we can quite comfortably say it's competitive with convolutional neural networks. We then used that classifier on a different malaria data set to see if the learning would generalize, and indeed it did. We got 94% accuracy in that, and so we can say that this approach, at least for the examples that we've tested, successfully carries learning from one data set to another and generalizes quite well. Okay, that's it.
Got time for one quick question ahead of coffee. Anybody got any questions? Everyone's keen for coffee. All right.
Well, so this whole thing is about relationship with human processing. So do you have any thoughts as to what, if any, relationship this has to how humans are doing things?
Yeah, so the operators that we use are very much based on the way that the human vision system breaks things down into shape, colour and texture, as has been mentioned earlier today. It's possibly more focusing on how the human vision system actually developed rather than how it operates as such. So obviously we developed it through a long-term evolution, and so this evolutionary approach is attempting to mimic that. And so I think there's a biological basis in that similarity to the human vision system.
Okay, great. So break for coffee now. Back here at 2:15.
Unfortunately, we've drunk all the coffee.
Oh, okay, sorry.
15-minute break, and then
So
Statistics. It's really difficult.
So we don't have HDMI or VGA. Is there a laptop we can put
What do you have on it? What's it got? Whatever that is. Do you have like a
USB stick. So you can
USB stick? Yeah, you can put it onto my laptop. That's fine. That would be great. Okay.
I have a PDF for
Yeah, whatever. Are you next? Are you the next speaker? Yeah. Which one? Oh yeah, that one. I'll try that. You got that first.
I mean, like, at least
It's all very
but you don't use him, and this is 4 eyewitnesses. You don't do like
I just research
Yeah, fine. Yeah, so
today's been great. It's given me a lot of development systems take a while. We've only really got serious testing. Especially right.
I'm sure you will.
it might be I can try the video and then got a dodgy.
So, yeah, I'm not from this station.
Yeah, it's come very hard.
Right, yeah, it's probably the same kind of like think like kind of next song that is really kind of
Which is good.
GP.
Yeah, she just doesn't like sort of
Amazing success.
Okay.
Yeah.
So we've got the horsepower. The thing about doing that is the ship change. So
yeah, and I'll remember
So I think one of the things